Okay. All right. So yeah, I'm Yoav Freund, and I want to pose an open problem that I have actually been working on for a while without success. So start at the beginning. So talking here about online learning in the most basic setting in a way, the set of decision theoretic online learning. And you have n steps. Sorry, n is the number of actions. Where is my? Yeah, n is the number of actions, and t is the number of time steps. And all of these, there's a bunch of algorithms that can achieve a regret bound where the leading term is square root of t log n. Okay. What did I do? I destroyed it. Okay. All right. So, and there's matching lower bound using random oblivious adversaries. So it seems like that's it. But it's not quite the end. Okay, so first part is I want to get rid of the n. Okay, so I don't like the n. Why? Because suppose that n is extremely large, so extremely large that even log n is extremely large. Then I would like to have small regret, not just with respect to the best expert, but maybe to the top 1% of the experts. Okay, so that's a natural thing to want. And if you have actions that form a continuum, then that's the only thing that you can kind of hope for. Okay, and so the desired form leading in the regret bound is going from square root of t log n to square root of t log 1 over epsilon. Okay, so that's improvement number 1. So there's a lot of work that has been done in all of these things, and I decided not to give any references. They're all in the description that you can get. But this is achievable. We know how to achieve this. Okay, so now the next thing is replacing t. That's a deeper thing. So actually, there's a lot of work that has been done on it. Starting with how to use expert advice, comparing to the best expert when the expert is very good, and so on. But I believe that the tightest characteristic is the second order bound that is in the paper by Cesabianchi, Mansour, Stoltz, and Stoltz in 2006. They have second order bounds, and they define, unfortunately, 2 types of second order bounds. Okay, these are both defined in terms of some kind of variance. How do you measure variance? Okay, so here is the most technical slide. Basically, these 2 ways of describing variance. One is, so basically the common thing is that the payoff sequence, we have a payoff sequence in some bounded range. Xi, for action I is xi1, xi2, and xi so on, going up to big T. And then there is a probability distribution over the actions that is defined at time t, so that the probabilities sum to 1. Okay? So these are the main things that we have. So the variance across time, which is the first thing that they define, is qt, where you take the sum of the squares of the payoffs across time for a particular action, for the action that is the best at that end time. Okay? So the expert that you want to compare yourself to. So that's one definition. And then there is another definition, which goes like this. Suppose that you look, this I call variance across time, because you fix one expert and you look at it across time. Variance across experts is that for time t, you just think about zt as a random variable that takes the value xit with probability pit. And now, as a random variable, you can basically ask, what is its expectation? Well, the expectation is exactly the payoff of the algorithm, right? That's by definition. And then you can define the variance, right? The variance that is the fluctuation around the expectation. Okay, so the variance of the payoffs, and then the total is simply summing them across time. Okay, and I really believe that this is the right definition and not this, and now I'll try to tell you why. Okay, so when you look, what I'm claiming is when you look along history for a specific expert, it has no meaning that it had a large variance at the time that nobody paid any attention to it. Okay? So suppose you have just two experts, one that is good initially, good, stays in the lead. This is the cumulative law. So he is good in the beginning and then just has 0 and goes on. And then the other one that has 0 and then is cumulatively increasing. Okay? And so at a later time, this expert down here becomes the leader, right? So you want to compare yourself to it. And then the question is it relevant that it had a large variance back here? It shouldn't be very relevant, right? Because it was not, nobody paid attention to it. Really, the only thing that is relevant is that they crossed. And they crossed once, and so you pay something for that crossing. Okay? So that's why I trust more in the other type of variance. Okay, so here's the open problem. Is there an algorithm for decision-theoretic online learning for which the leading term in the regret bound for all payoff sequences and for all epsilon larger than 0 is this? Is this, right? So instead of time, you have cumulative variance, and instead of number of experts, you have epsilon. And this is the important thing, is that epsilon, you don't need to decide on it in advance, right? It's not like n, that you know what n is. This should hold for all epsilon at any point. And Vt is some kind of intrinsic measure of time, if you will, right? It tells you how much really switching around has happened, and that's instead of just time, right? Because it might be that there is a long time that all of the experts basically do the same thing. So there's no reason to pay for that time. Okay, so that's basically the open problem. And I went actually through several versions of this, and I know that it's not easy to find on the web, so I put on my homepage, I put the open problem right down here. So you can, if you want to know the details, you can actually get them, because the one that you find on the site is, I improved on it, let's say. Okay, so that's it. Oh, $500. Any other questions? No?